Thanks for attending this presentation. My name is Alejandro Mera, and today I will present DBOX, DMA-enabled Compartmentalization for Embedded Applications. This project was developed in collaboration with Jihui Chen, Ruimin Sun, Engin Kirda, and Long Lu. The outline of this presentation includes an introduction to embedded devices, the motivation of this project, details of DBOX design, implementation, evaluation, and some conclusions. So, embedded devices are ubiquitous and adopted in critical areas. For example, in intelligent factories, healthcare, smart homes, and the automotive industry. Because of the importance of these devices, they are the target of major attacks, disrupting essential infrastructure. To defend against these attacks and mitigate vulnerabilities, the security community has developed methods based on static or dynamic analysis, attestation mechanisms, and compartmentalization, which is the main topic of this project. Compartmentalization assures the principle of least privilege and restricts attacks or crashes within specific boundaries. Besides the benefits of compartmentalization, the state of the art in this area is limited. It is imprecise because of static analysis limitations. It is impractical because it requires complex security policy definitions. It is incompatible with real applications because it requires hardware modifications that are not available commercially. But something that is more concerning is that these solutions ignore or barely support DMA operations. Why supporting DMA is fundamental. Let's take this smartwatch as an example. This device usually have two types of data flows. The first one uses slow communication channels through MMIO operations that are protected by the memory protection unit. The second type of data flows use DMA-enabled communication channels, which, for example, are used to write data streams with high throughput and high performance. Also, DMA-enabled channels are used to read data from peripherals, while the core processor is in the power-saving mode, which is quite important for battery-powered devices like this smartwatch. Besides these characteristics, DMA has security implications. For example, a confused deputy vulnerability can be exploited to force the DMA controller to read and exfiltrate data from memory areas that were not meant to work with DMA. In general, if the DMA controller is compromised, it can read or corrupt any memory area because the MPU does not interpose any of these operations. To solve the current limitations, we introduced DBOX, DMA-enabled compartmentalization for embedded applications. DBOX defines a reference architecture and a systematic approach to enable DMA operations. Our approach includes procedures for MPU region configuration, DMA controller reconnaissance, kernel hardening, DMA policy definition, and signal and exception handling. DBOX architecture is based on FreeRTOS-MPU, which is the most popular RTOS for deeply embedded devices. It defines tasks as the unavailable compartmentalization, which are configured during the development phase. DBOX also uses a capability-based security policy that provides strong security properties. This is an example of the capability-based security policy enforcement. In this case, task number 1 is the owner of 3 capabilities for USART, SPI, and ADC peripherals. Let's say that task number 1 sends a request to read the USART peripheral through DMA. Because task number 1 is the owner of a capability that grants read permissions on USART, then the security policy is validated and the DMA task configures the DMA controller for this operation and lets task number 1 to read from the USART peripheral. On the other hand, if task number 1 requests to write on the USART peripheral through DMA, Then the security policy validation fails because task number 1 does not own capability with writing permissions on user. Also, the failed validation will trigger an exception that is handled by debuggs. We use the capability-based model because it mitigates confused deputy vulnerabilities by design, which in comparison to other models like access control release, mitigating this type of vulnerabilities requires complex validations that are error-prone and not suitable for embedded applications. We developed a prototype of debuggs for the Cortex-M3 FreeRTOS-MPU version 10.4.1. The total implementation is around 1400 lines of C code, including the DMA task and the kernel extensions. We also use simple C code structures to define the security policy, like the example that is shown here, which echoes our design goal of applicability on real applications. For example, these capabilities have object references to some peripherals in the MCU, and here we have access rights for reading or writing on the peripherals. We evaluated debuggs from 3 perspectives. The first one, security; the second, performance and power requirements; and the third one, applicability on real-world scenarios. Our evaluation setup includes the development board Nucleo L152RE provided by ST Microelectronics. This development board implements a Cortex-M3 MCU running at 32 MHz. It has 512 kilobytes of flash, 80 kilobytes of RAM, and 2 DMA controllers. The baseline that we use to compare our solution is vanilla FreeRTOS 10.4.1, and also the hardware abstraction library HAL for peripheral drivers that is also provided by ST Microelectronics. The tooling, we use Percepio Tracealyzer for collecting performance metrics, and the power monitor provided by Texas Instruments to collect electrical metrics. For the quantitative analysis, we use the memory region ratio metric, which measures the effectiveness of a compartmentalization solution. Specifically, this metric calculates the ratio of the memory areas exposed when a given task is executed to the total size of the memory area. We observe that debuggs reduces the region ratio to 0% and 1% for peripherals and user space flash and memory areas. Debuggs also maintains 0% of the region ratio for kernel space. The reason for this result is the numbering scheme of the MPU regions that we define in debuggs design. Particularly, kernel memory areas use the higher number MPU regions, which cannot be override by user-defined regions because they use lower MPU numbers. In terms of return-oriented programming gadgets, the implementation of debuggs only add 10 new gadgets. It also exposes 13 gadgets from user tasks, which only represents 2.4% of the total number of available gadgets in user space. This result is also related to the stricter debuggs MPU configuration. We also perform a qualitative analysis comparing debuggs with state-of-the-art solutions. The result here shows that debuggs has complete and intrinsic support for DMA operations. The only solutions that partially support DMA are Microvisor and TalkOS, but in the case of Microvisor, it is already deprecated, and TalkOS does not consider the diversity of the DMA controller, which in turn can overexpose sensible memory areas of the DMA controller. It is important to notice that debuggs is the only one that supports extensible access rights, which are meant to handle off-chip peripherals connected to SPI or I2C buses. Without considering this addressing scheme, the DMA operation is incomplete. For performance analysis, we conducted a micro benchmark which analyzes the impact of DBox on the kernel operations. Specifically, we observe a low overhead of 1.74% for the context switch routing. Also, we conducted a macro benchmark, which are operations reading and writing from peripherals through the DMA controller. Here we observed an overhead inversely proportional to the data length. For example, here in this figure for the SPA transmission, we observe that for 1 byte the overhead is 134%, but for the same operation for 50 bytes the overhead is 10%, and for 100 bytes the overhead is almost 0%. This is an expected result because DMA is meant to transmit high throughput data streams. So if we use DMA for that particular operation, then the overhead is negligible in this case. For power analysis, we use the same macro benchmark operations on peripherals that I explained previously. Here, DBox reduces the power requirements on average 16%, 17%, and 18% compared to pooling, interrupt, and insecure DMA methods provided by the vendor's HAL drivers. And the reason for this result is that the baseline drivers provided by the vendor are developer friendly but not efficient. On the other hand, DBox uses low-level drivers to access directly the peripherals, which requires more engineering effort, but they are power efficient. Finally, we tested DBox in a real-world scenario, securing a Programmable Logic Controller or PLC. The original application was totally monolithic, so that if an attacker takes control of the communication protocol Modbus, the whole PLC is compromised. To mitigate this risk, we applied DBox procedures to create 2 compartments supporting DMA. The first compartment contains the communication protocol, and the second one contains the control logic. The result of this test is that the DBox improves the security of the whole system, reducing the attack surface. Also, it maintains the performance of the real-time operations and the scan cycle of the PLC, and it reduces the power consumption of the whole system. Conclusions: DMA operations are fundamental for embedded applications because of performance, power, and security implications. DBox provides a systematic approach to enable secure DMA operations for compartmentalization solutions of embedded applications. DBox can improve the security of real-world applications, adding negligible overhead and reducing its power consumption. Thanks for your attention. This is the end of my presentation.